Good morning, guys. Well, technically it's closer to noon and I'm starving. However, the show must go on. I hope this sounds okay. I'm in a room. It almost sounds like I'm in a recording studio. But anyways, we're going to go over voltage today and a series circuit and maybe parallel. I don't know. We might do that on a different video. So you look here. I have my meter and it's set to voltage DC. DC looks like the little passing lane you'd see on the freeway or road. This would be alternating voltage because the waveform represents alternating voltage. Here's ohms, no power to the circuit, and here's your amperage side. So on this one, we're going to focus on our voltage and how we would look at a circuit and how voltage acts within that circuit. So I got my leads. Got my correct setting. I created this circuit. Here's my switch. I have a fuse. Turn the switch on, the light bulb lights up. Very simple one load circuit. And we're going to check our voltages. So, with any diagnosis, you would always want to check your battery supply first. So, if you look here, this is my 12 volt battery supply. This is my positive. This is my negative. So I have 12.06 volts in this circuit here. With this switch open, because it's open right now, think of a drawbridge. Bridge is open, no cars can get by. Sorry, there's my horn. Closed, open. Closed drawbridge, cars can drive by. Open drawbridge, no cars can drive by. So think of the cars as your current, your flow, your atoms. If the bridge is open, no go. So right now my switch is open, the light is off. Battery voltage is 12 volts. I want to show you guys down here. Can't quite see it. This is also a ground. If we were to put our lead here, it reads 12 volts, 12.6 volts. That is because the circuit is open. So there's voltage present all the way up to the open. So I'm going to leave my ground here just to make it easier for you guys to see. And my positive lead there, giving us 12.6 volts. With this circuit the way it is, I should have voltage present all the way up to this point here. Okay? Why? Because it's before, let me turn that real quick for you guys. Because it's before the switch. So voltage, current, no current because current can't flow in an open circuit. Voltage leaves the battery, goes to this point, 12.6 volts, goes to this point through the fuse, 12.6 volts. Now, if we were going to see 11.5 there, that would mean somewhere between here and here, we're dropping voltage because all voltage has to drop over resistance or load. And we could check that by going here and here, and we have 0.00. So there's nothing being lost in between this whole section here. If we were to continue to this point here, what do you think we'd see with the switch open? Go ahead, take a guess. I'll act like I can hear you. Very good. 0. Because nothing is going to pass that open switch. Now, if we were to close that switch, just like closing the drawbridge, we would have voltage all the way up to, on this case, the load. And after that load, we should see 0 because this load is going to use up all of that available voltage. So let's check it. I'm on my ground. I check here. 12 volts. Check here. 12. Oh, look at that. We have a little bit of voltage drop because we had 12.06 to begin with. Sorry. Now I have 12.04. So it would be curious to see where we're losing 0.02 of a volt. Come here, we should see 0. We have a little bit right there on the meter. That's just enough to push it back to the battery. But in automotive diagnosis, that generally means nothing. Come here. look at that. We had 0.01 in this wire. 0.01, come to here, the ground, 0.000. So that little bit of wire has a little bit of resistance in it. The voltage has to drop across it. Now the circuit's taking everything. What if we were to add another resistor into this load? Still in series. There's still only one path for current to flow. I don't know if you can tell, but those light bulbs are considerably dimmer than before. Now let's do our checks again. We should have, how much here? Good, 12 volts. How much here? Good, 12 volts. How much here? 12 volts. Oh, there's that 0.04 again. Now, what do you guess would be our voltage here? Oops, I hope you didn't see that. Right before we go into our last light bulb. Think it'll be half? Very good. 6.37, whatever. Here, go here where it's more secure. 6.37 volts. That means this light bulb used up half, where this one, before it and after, this should be 0.01. Oh, 0. This wire doesn't have any unwanted resistance in it. So we can see how voltage drops, like we talked in our lecture, across each of those light bulbs. Let's go ahead and add another one in. It's still a series circuit. Yeah, well, they're even dimmer, but I don't know if you can see it. It's still a series circuit because there's only one path for current to flow. If this light bulb goes out, they all go out. So, let's check our voltages again. 12.05, 12.04. Oh, something's heating up. Oh, what do we got? 8.07 coming out, what's left on that one. So it used up 8, 9, 10, 11, 12, 4 volts. And then to this one, 8.07. And after it, 4. So it's using up 4 volts. Before the last one, 4. And then after, 0. So all those voltage drops, if you wrote them up, 4, 4, and 4, should equal up to be 12.06 in this circuit. So that is a voltage in a series circuit. Now let's say you just wanted to do a voltage drop across one load. Take your 2 leads and put them across that load. And we already knew what it should be because we checked it in the circuit from the top, from the power source to the ground. So across this one load, this one light bulb is using up 4.05 volts. 4.00 volts. 3.96. So you can see if you were to add all those up, granted the 0.96 is almost 4, you would get a total of 12 volts, or what we started with. So that's voltage drop, source voltage, checking your battery, an open load test, right there, 12.06. Always check your battery first before you do any diagnosis, or none of this is going to work.